Now, in the next 15 minutes so, I will share my recent thoughts on how to connect information theory and deep learning together. It's my belief that the IT community cannot afford to be sidelined in this current AI code rush. On the other hand, deep learning can also benefit significantly from input from the IT as well, as we will see hopefully in this talk. Okay, so the title of my talk today is Information Theory Inspired Deep Learning. So I'll start with brief introduction to deep learning and its problems. So then we'll think out of the box and look at deep neural networks from completely different perspective, particularly from information geometry perspective. So once you have that perspective, then you know that, oh, the DNN can also be evaluated in terms of information quantity along with the standard error rate or accuracy. So then we talk about the condition mutual information constrained deep learning and knowledge distillation amplified deep learning, because initially I also want to cover the so-called the KD resilient deep learning, which is quite interesting and which can show that I think that's perhaps the only way from the IT perspective to show that indeed you can build a large DNN model which cannot be distilled by this KD. So the IP of that model cannot be utilized by your competitor. Okay. On the other hand, you can still provide service. So let's now look at this deep learning. So to understand deep learning, we can ask two questions. So number one, what is DNN? Number two, right? How is DNN trained? So let's look at the first question. So what is DNN? Now, of course, different people may have different answer. Now, from engineering perspective, we can say DNN is simply a cascade of layers of neurons with millions, billions, or even trillions parameters, which converts an input X into a probability distribution Q sub X over the set of labels. So in this context, I'm talking about the classification DNN. Okay? Then given the input X, the predicted label is either top one label, which has the largest prediction probability from this Q sub X vector, okay? Or a random label denoted by Y hat, distributed conditionally according to Q of X, so given X. Now, normally the performance DNN will be evaluated according to the so-called error prediction, right? So it's not equal to the true label. Okay. Now, how's DNN going to train? Well, to train DNN, mathematically, we just need to solve this really complex optimization problem. And here, the minimization is over the parameter space. So which now is million, right? Trillion dimension. Now, this expectation is with respect to the distribution of your training set. But the goal, okay, even though we minimize this object function, but the goal is to make sure that the error rate over the testing set is kind of small. So in this aspect, you can see you do see a little bit mismatch, okay? So because the training, the objective function will be minimized over the training set, but on the other hand, your goal is to want to make sure that the error rate over testing sets can small. Now, in the conventional deep learning, this object function is given by the so-called cross entropy between the one hot probability vector corresponding to the true label and your predicted distribution Q sub X. Now, this term you can see from in the statistic community, right? You can easily recognize, well, this quantity is just simply negative log likelihood. So in this sense, you can see, so deep learning is more or less equivalent to maximum log likelihood estimation. Okay, so of course, it's a huge optimization problem. Now, what are problems? Well, I mentioned this mismatch, right? So mismatch between the training set and the data set. So this is really reflected by this error rate. So the error rate DNN depends on the joint distribution, right? And so a low error rate for one joint distribution does not guarantee a low error rate for another one. So this is a mismatch. So this match, if you read it abstract, then this mismatch will also incur this kind of problems. One is overfitting, the other one is robustness, and or you can put another way, the security. Okay. Now, even suppose we solve this mismatch problem, right? Suppose that the you somehow train the DNN, okay, which can achieve quite a low error rate across all kinds of joint distribution. Then still it's a problem because it remains black box. So we don't know why it works, how it works. So in the end, so you have really the problem, lack of deep understanding. So you put them together, you can see the major problem in this current AI is like this. One is AI security, the other one AI interpretability, and of course performance of the issue, right? Now, how are we going to address this issue? Well, once again, we need to think out of the box. So next, I present some information theoretic perspective, okay, to address this kind of problem to a certain degree. Now, first, right, we need to now go beyond, okay, so go beyond error. So this is why I need to introduce information geometry into the DNN. So we look at DNN from different angle. Now, here's analogy, right? So at university, we examine student, right? We ask them to take test, then we know the score. And so this is similar to DNN, right? So once DNN is trained, so how do you evaluate? Well, we just evaluate DNN over validation set, or sort of a testing score, short testing. But we also know that, right? I think a lot of students with really good transcript may not too well once they move to the workplace or move to the industry or move to even some academia, right? Why? Right? Well, because, well, then the testing score do not really represent everything about student, right? So this is why people look at the EQ or social discipline as a trait. Now we need to ask the same question with DNN, okay, right? So error rate, I mentioned before, error has a problem, okay, right? So then how are we going to discover other kind of structure properties, mapping structure, okay? So this why then we do the kind of abstraction. So I think this is also similar to what Shannon did when Shannon created information theory, right? The whole communication system is really complicated. How do you investigate communication system? Well, Shannon did abstraction. Here, I do abstraction as well. Well, first, let's put aside the physical architecture, so the neural architecture side, physics side. So in this case, then we just simply regard DNN as mathematical function, okay, high-dimensional mathematical function, and mapping from X to this property distribution in the whole property space. Now let's focus on this property space. So then you can see that the DNN outputs form a different distribution cluster, one cluster per label. We want to understand the information geometry of this cluster. For example, on the right, I draw this kind of the illustrated graph, right? You can see we have cluster, each cluster per label. Now you can see, so can we say, is there any centroid of this cluster? How to define, how to compute? Now, once you have that concept, so can we say, okay, can we define the concentration? Okay, so intra-class concentration, but how do you measure it? Now, for different cluster, can we measure distance, right, between or among different cluster? So that's got inter-class separation. How to define, how to measure it? So now we answer this type of question, okay, from the information theory perspective. How? Well, we take one step backwards, okay, Now look, little big picture. So now we do another layer abstraction. So now we embed the DNN into Markov chain. Now in this graph, in the middle, there's input or input DNN, which you can model as a random variable or those very high dimensional, right? Random vector. On the left, you have these two crown tooth label, which is unknown, right? At least it's not visible to DNN, otherwise you don't need DNN, right? So this one then, so we assume there is underlying, okay, underlying transition probability distribution from Y to X, which is also unknown, right? Then you have DNN in the middle between the space X and the output probability space. So this one was Y hat. We defined I had before, right? So given X, then you have one point in this probability space. So that is probability distribution. Now, once you have the distribution, you get to the random choice, right? According to the distribution, that's a Y hat. So in this big context, you can see, oh, this Y, which is unknown, and X is input to DNN, and Y hat is randomly picked label. So these three form a Markov chain. And the corresponding probability is given by here, right? So the condition probability of Y hat given random variable X and Y, right, with a specific value, well, it depends only on this input X, okay? And this one, once X given, so this one is equal to this output distribution, right? Okay, so keep this in mind. And sometimes you also write this Q sub X of I as a Q sub Xi given X and theta, okay? So because, because theta later on we need to optimate and find theta. So with this Markov chain in mind, you just visualize this in your mind, okay? So with the Markov chain in mind, now we can define the centroid, we can define the concentration, we can also define the separation. Now what's centroid? So given this unknown label Y, it's quantity label. Now, of course, from small y, you can jump to this input X, right? So input X is random, it's random. So the DNN will map X into the distribution, right? So then as a result, so this Q sub capital X is a random distribution, it's a random point in the space. So the all instances of this Q sub capital X then form a cluster in the space. And this cluster is corresponding to a particular label Y, right? Then naturally you can see how to define this centroid. Well, the centroid can be a defined centroid as a condition average of all these instances in that property space. Okay, given this unknown label Y. Well, this it turns out, so this centroid is exactly, okay, later you can, this centroid is exactly the conditional distribution Y hat, random variable Y hat, given Y, because you need an average of all possible input X, right? So that's centroid. So back to this graphing is, oh, now we have the centroid, right? Now how do we measure concentration? Well, because each point distribution, now I can measure the distance between this each point and the centroid according to KL divergence distance, right? If you do that, then the centroid, it turns out, so that average is exactly the conditional mutual information between this input random variable X and this randomly picked label Y hat given this ground truth label small y, okay? So let's walk through this. You can see, well, according to mutual definition, right? So this will be the condition between X and Y, okay? The multiple what? Condition distribution Y hat given X and Y, right? Then the logarithm of the ratio between the condition proposition Y hat given X and Y over, right, this condition probability Y hat given capital Y, okay? Now, because of Markov chain, we know that, so this one is exactly equal to Q sub X of I, all right? So this one is outside expectation, well, this summation is simply continuous expectation. Now, this inside summation is exactly equal to the co-divergence between these two distributions. So one is this, okay, random mapped distribution Q sub X. The other one is the centroid, right? Now to recap, now then this conditional mutual information between X and Y hat given Y then quantifies the concentration of the cluster corresponding to label Y. Okay, so let's now move on. Now, because Y label Y is also random, so you need average of all post cluster. So then you got this mutual information, right? Mutual information between X and Y hat given the random variable Y is not specific. The label is a random label. So that's our definition of conditional mutual information. So then you can see, so this conditional mutual information measures the average concentration across all clusters. Now you can see, so this quantity has physical meaning in the probability space. So later on, we attach semantic meaning to this quantity as well. Now, how do we measure the separation? Well, there's so many ways we define. But whatever quantity define, you have to make sure later on this way for utilize quantity in this current the GPU-based parallel computing platform. So I tried many different type of quantity. Then it turns out so this definition is good. Okay, so so in my full paper I defined quite a few. They're equivalent, but this one is convenient for the subsequent GPU-based optimization. So how do you define? Well, we define the so-called inter-class cross entropy. So you see, I take one distribution from one cluster, so the represented by Q sub capital X. Then I randomly take another one, okay, another distribution from another cluster, so which is represented by Q sub capital U. So I compute cross entropy, okay, and take average, and we call this one this separation. Use this one to measure separation. And indeed, you can see once this number goes up, the separation distance between cluster in the probability space is also increasing. So now we have defined this information quantity. Okay. Now at the end can also evaluate it in terms of information quantity in addition to the error. Right. So the similar to okay. Now we can I think we can evaluate, we can judge, right, a person, right? Okay, not only in terms of transcript, but also in terms of it is other personal trait, right? So this one you can see this is related to the mathematics structure property, so not the physics structure, right? Because in the end, it is this mathematical structure that really matters. So even though the physics structure is important. Now before we evaluate at the end, according to information quantity we just introduced, I do another layer of abstraction, okay? Exactly as Shannon did. Now further abstract the end as a channel, you see? Now this channel has two inputs, right? So one is input to dnx. The other one I now recall this parameter vector, which is a huge dimension, it's not the input. Then you have this output predicted random label y hat. So this is a channel. So for this one, you can see we also define information quantity. Now we control something in parallel with two well-known problems in information theory. So one is got rate distortion problem in information theory. Now we have something similar. So rate distortion problem in deep learning. So we want to minimize, right, this conditional mutual information over all possible parameter vectors subject to certain DL constraint. Okay. Then we can also maximize this conditional mutual information, right? Once again, over all possible input, right, parameter theta subject to other DL constraint. So this is more like capacity problem in deep learning. And later on, you can see, so these two problems have corresponding to different type of information theory inspired deep learning paradigm. Okay. Now, before we discuss first one, so let's now look at how do we evaluate, right, at the end in terms of information quantity. Now, ideally, we want to have really small value of this CMI, which represents concentration, right? Because the cluster is really concentrated, collapsed to one point, that will be ideal. In the same time, we want to maintaining or even enlarging, right? So this separation. Okay. Now, but that's two quantity. Then I want to deal with one quantity. So then I define this ratio. Okay. So this got normalized condition mutual information. So then when this one decrease, so this one decrease, right? When this denominator goes up, or this normalized CMI is also decreasing. Okay. Now let's now evaluate DNN according to this information quantity, right? So here we evaluate standard well pre-trained models on the ImageNet. Now once, so this is the, I think the same family model represented by same color. Okay, so this column represents CMI value, and this column represents the separation value, and this one represents the this column represents the normalized CMI value, and the last one is error rate. You can see, so when this number goes up, like the model size also increases. So in general, at least for this ImageNet, okay. So model size goes up, CMI value goes down, separation value also increases, and NCMI value goes down. With one exception is in this efficient family, like this efficient net B naught. Okay, you can see. So in this case, so even the B naught is simplest one among the four, but this one has the largest separation. Okay, and but also they have largest CMI, so the ratio is also then is the largest one among this. Okay, of course. So you see a little bit trend like this, but when you evaluate this kind of model over the another well-known training data set, got the C5 100, you see more or less, but it's not exactly like this. But one thing is common: when you pay attention to the column corresponding to CMI, NCMI, and error rate, then you find something really interesting. Okay, for the both data set. So as long as CMI value decreases, the corresponding error rate also decreases. Okay, so to show this one, I can show you another graph. So this one. Now in this graph, you see three things. One, so this horizontal represent this validation set, okay? NCMI value over validation set. Now vertical represent the error rate over the validation set. Now you look at the circle, right? The circle thing represent the size of the corresponding DNA model. So we're more like a physical property, a physical structure. Now you can see, so the physics thing really does not, well, it's important, but does not really matter, because sometimes you can see small, right? Small circle, small model can perform better than this large one, right? Okay. So I think this once again, a couple of what I mentioned earlier, it is the mathematical structure that matters most, right? Now, in this case, you can see, so there is strong correlation between the NCMI value and error rate. So this one is more like linear. Okay? If I calculate the corresponding correlation, the correlation is greater than 0.99. Now, for the other C5 100, the correlation is also greater than 0.98. So you do see this kind of linearity. Okay, but this is the NCM value. Now this motivates us, okay, well, in addition to trying to minimize the cross entropy, now probably you can also minimize the CMI. Well, with this, so then we got this so-called CMI constrained deep learning. Now in this case, we will minimize, right? Minimize the CMI. So we got this optimization problem. Okay. So this one, the first one, the E sub capital X. So this term is a traditional cross entropy, cross entropy loss. Now, in addition to minimize that, we also want to minimize this normalized CMI. Okay, it's new constraint. So you can see, so this problem you can see more or less similar to the rate distortion problem in information theory. If we interpret this NCMI as kind of rate, and this traditional entropy cross entropy loss as distortion, well, it's more or less extended rate distortion problem. Of course, it's limited because you do not have the freedom to select this Q sub X, right? Because this Q sub X is constrained by the physical structure of DNN. So you cannot freely choose this condition distribution. Okay, so that's difference. Right? Now, to solve this one, we apply standard approach. So we apply Lagrange multiplier method, right? And convert this constraint into this unconstrained optimization problem. Now we have three terms. So the first term is this traditional cross entropy term. The second term is CMI conditional mutual information between X and Y hat given Y. And the third term now is subtraction, it's negative, okay? So this one is separation, rapid separation distance. So conceptually looks like, oh, it's nice because you have a nice optimization problem. Is it easy to solve it? The answer is no, not according to this form. So why? Now you look at this three function in this overall objective function. You see? So the first one you can see. So this one, see xy is represented by training set. Okay, e sub x, right? So this e expectation is summation. You see? So then this function. So the first one, well, you can say is sample instance additive. So as a result, so you can run this parallel computation via GPU. So this was GPU is not so expensive, right? Because development require GPU to train DNN. So that's because this one now you can. So this one you can, because each this cost function. There's no structure, so you have to compute this value for sample by sample. Okay, so this way you run it this in so-called mini paths. You can run it in parallel. Now for the third term, well, this cross entropy function, the interclass cross entropy function, well, it's also sample additive. So that one can also fit well. Okay, can also fit well to the parallel computation via GPU, but not the middle one. Okay, because middle one you go back to the early visualize that the probability space, right? That geometry. You see, so this conditional mutual information represents kind of overall structure, right? So it's not sample instance additive. And how to solve this one? Well, in this case, we apply the same technique information theorists are quite familiar with. That's in the Plackett-Array model algorithm for computing rate distance function. Exactly similar idea, okay? So to do this, right? So this I mentioned before. So the original format is not amenable to parallel computation via GPU. So how to overcome this? Now we have to convert the second term to a form so that you can compute in parallel via GPU. So to this, we introduce some dummy distribution. Okay, so this is related to the divergence inequality, right? So introduce dummy distribution. Now I can convert the single minimization into double minimization. Okay. Now the first term is same as before. The third term is also same as before. But the middle one, so once we introduce this dummy distribution, now that mutual information, so that's mutual information term, this term, okay? I hope you can see my mouse, okay? So this term can be written as this expected value of this curve divergence between this output distribution from the DNN and this dummy Q of Y, right? So Q and because now this function now is, you see, is the sample additive. Now, of course, this one itself is not equal to mutual information, but once you minimize over this Q sub C, so this minimization, that is equal to this conditional mutual information. So with this one now we can apply the stochastic gradient descent algorithm to solve this problem. In addition, by using this alternating algorithm, because we fix this QC, we try to minimize theta, and that can be solved by the statistical gradient descent method, right? So once you QC, they can come back to find Q sub C analytically. So we have this alternating procedure. So in theory, if you can do this will converge in theory, okay? So with this one, let's now show you some result, right? So this we test this over CFAR 100 data set, also image data set. Now you can see that compared to the traditional DNN trained with C loss, so this is much better. Okay, because I think for this one probably gain is 1.3%, because nowadays you get 1%, 1.3% gain is kind of huge gain. Okay. Now also this is better than all the other kind of method based on the concentration separation in the intermediate layer. Okay, so this one I think you can read on the screen, so I will not go into the detail. Okay, and the same thing can be said about this ImageNet, right? So this once again, so the model trained with CMIC framework also gives best result, right? Now, what is more interesting, I think, is now you can see that we have a little bit understanding, okay? So this one you can see we showed the final, the cluster from two methods, right? So one is traditional CE loss, the traditional DNN trained with CE loss, and the other one is the DNN trained with this information quantity now, CMIC. So now you can see visually, you can see that suddenly the DNN, right, trained with the CMIC constraint indeed is better, because you see it's more concentrated, right, and far separated. Okay. Now I want to attach physical meaning, not physical meaning, so to the semantic meaning to CMI. So in the past, in the context communication, we always had the impression that so information quantity have no semantic meaning, right? Because we talk about random variable, it's already randomness, right? So we only say, okay, information quantity only have meaning in Shannon sense. Okay, now it's different. Now on the screen, you see bunch of images, right? On the left, on the right. So on the left, we did inverse mapping. So remember DNN, right? Mathematically, it's now mapping, right? From X to a probability distribution in the probability space. Now we do the inverse mapping. So given the centroid of each cluster, so we try to map the centroid back to the image space. So this one you see for this fish, right? We got two. Okay, we applied CAN method to create this inverse. Okay, so this you can say so this image are corresponding to the centroid, right? And on the right, those are natural images. Similar for these two birds. Okay, no, actually now when I interview people, I also apply using this picture to test people's intelligence. I ask them, okay, can you tell me so which image is generated by AI? Some good smart student can answer, and others cannot. Okay. Now you can see. Look at this bird. Okay. So the two left one are AI generated inverse problem corresponding to the centroid, right? And the three on the right is natural image. Now you also see number on the top, right? On this top left corner, okay? So that's the corresponding KO divergence. Now I think you can tell, so this KO divergence is quite meaningful, right? You see? So for this one, you can see it don't have much context. So this one, you can, oh, this number is a little smaller. And for this one, for a little more context, you have little large KO divergence value. And this far right one, you can see really complicated background, right? And this one has largest the CMI value. Okay. Now you can see, so in this sense, so when you map this probability space now back to this image space, now what's meaning of CMI? So CMI actually quantifies the contextual information around the object you want to recognize. Okay, so let me say it again, because this will read the introduction to the other problem. Okay, so the semantic meaning now in the image space of CMI is that CMI now quantifies the contextual information, with context, right? Contextual information around the object you want to recognize. Okay, So the larger the CMI value, and the more complicated of the surrounding environment or the contextual information. And this is really useful to our the subsequent problem. Okay, just keep this in mind. So let's move on before we talk about the next deep learning paradigm based on information theory. Now you can see, applying this information quantity, we can also now visualize the whole learning process. So in the past, it's kind of complicated because this is a black box, right? How do you understand this? Now you can see I can also visualize the whole learning process. Here, trying to show some video, okay? So you can see at the beginning, so we compared in parallel, I guess, one training process started with this cross entropy loss function, another training process with this CMI constraint, okay, object function. So at the to begin with, you can see here we just took 3 random classes, okay? You see all those at the beginning because you randomize theta, okay? So as a result, then the initial DN cannot distinguish anything. So everything will be collapsed into one, into the center, more or less in the center, right? So now you can see when you run this, now you can see this running process. So all those samples will move around, get pushed to the different corner, right? So this is what illustrates the whole learning process. And you can also see the corresponding CMI value and the corresponding separation value. Okay, now you can see, right? So in general, you can see that. So in the learning process, in our case, right, the CMI value is always under control, right? On the other hand, in the traditional deep learning, the CMI initially shot up quickly, okay, then it's coming down. But our curve is always below the CMI curve in the traditional training. Now, on the other hand, look at separation. So initially, right, separation of the standard training will go up quickly, but eventually the separation in the CMI deep learning will surpass the curve. As a result, the ratio becomes smaller. Then you will see the difference between these two pictures, right? So the right one, certainly each class is more concentrated, right? And they're all quite separate from each other compared to the one on the left, okay? So with this one, let's now move to, okay, I need to jump to, let's now part 6, okay? So now we are talking about capacity problem in deep learning. So this is related to what I call the knowledge distillation amplifying deep learning. Okay, first, let me describe what is knowledge distillation. Initially, knowledge distillation was proposed as a method for model compression. And so later on, I think Jeff Hinton popularized this one. Now this KD is widely applied in post-industry academia to train a small model by leveraging some large model, okay? So what's KD? Well, KD distills, look at this diagram, okay? So KD distills large pre-trained model called teacher into a student. This later on becomes distilled student, so that this distilled student will perform better than the student trained on its own, okay? How it works? Well, look at image, right? X, you feed image X into both teacher and student, and teacher got its own output Prof distribution. Then you further apply so-called power transform, which is introduced by us, because in the original one they need to go to the layer. I think that's a logic layer, so to the template scaling, and we show that the template scaling and power transform are equivalent. Okay. So then you do this one, then you pass this power transform distribution into this KD loss, right? So you can see the KD loss now has 2 terms. So one term is the original conventional cross entropy loss. Now this one's got distortion loss. So this one just co-distance between power transform teacher distribution and the power transform student distribution. Why do you do this? Well, I think the purpose, so now teacher's fixed. Now training process simply train the teacher, where you find the theta sub S. So once you have this distortion loss, then somehow this the training process can utilize this power transformed teacher distribution to guide the whole learning process so that the distilled student, in some sense, can mimic the behavior of the teacher. Okay, so this is more like high-level understanding. But in ask a lot of people question, still people don't understand. Okay, so why does KD really help, right? And even to this stage, I don't think say then the community has really well understanding this one. I think the Jeff Hinton called this power transform teacher distribution as dark knowledge. Dark knowledge can help, but dark knowledge, what's dark knowledge? Right? Now, with this information quantity, particularly with the semantic meaning of CMI, now we can shine new light into the question, okay? Into the following question. Why does KD work, right? Well, we have this. Next slide, okay? So let's go back to the image. Now, for simple image, we can say, the image contain probably two type of information. One is really the object, right? It's ground truth, okay? It's prototype. Now, around this object, we have different background, okay? It's background we call contextual information, CI, right? Now, as I mentioned before, right, with the CMI, we know that, okay, so this CMI can quantify contextual information. So in some sense, so the CI, some contextual information is provided by the teacher to the student while the distortion loss through this power transform teacher distribution. And we know that this contextual information, right, can now be quantified by CMI. And indeed, we further verify that because in the KD, in the original formulation, the version popularized by Jeff Hinton, they introduced temperature. So what's purpose temperature? Actually, it turns out the purpose of temperature scaling or the power transform on the teacher side is simply to increase the CMI value. Okay. Now we know CMI has this semantic meaning, right? CMI quantify represent the contextual information. So that means in order for the teacher to help the student even more, then probably we need to find a way to further increase the CMI value from the teacher. So this motivated us to consider the KD amplifying deep learning. Okay, so then what's objective? Well, our purpose is to retrain the teacher. So we don't touch the KD method. We simply retrain the teacher to amplify the KD effect. How? Well, now we retrain the teacher to maximize the CMI while minimizing CE loss. So that the teacher can convey more contextual information to the student. Okay, so this idea really comes from the semantic meaning of CMI. So now the retraining process is equivalent to solve this minimization problem. You see, now still maximization is not maximization. Okay, maximization problem, maximization over all possible parameter vectors, right? Now the first term now change negative sign because this is maximum, right? So it's a negative sign minimum because we're still on the minimum CMI, minimum CE loss. So the first term is still the cross entropy loss, right? Now the second term is now the conditional mutual information. So we want to maximize this one, okay? So let's take a moment to look at this optimization problem. You see, so this one is now equivalent to more or less, right, equivalent to the capacity problem in information theory. So in that case, we want to maximize mutual information, right, between the channel input and output. Okay, so this one you can see is more like a capacity problem in deep learning. Now, how to solve it? As before, so this format itself is not amenable to the parallel computation via GPU. As a result, we need to further modify this object function. Okay, how do you modify? Well, now we need to apply same type of trick. Information theorists are quite familiar. So that's we apply, right? We introduce so-called backward channel. So exactly as in the Plafford-Arimoto algorithm for computing channel capacity. Okay, so I list a little bit math derivation. I walk through quickly. Okay, so this written object function, right? Cross entropy term, negative cross entropy term plus mutual information. So this one is not convenient for the GPU computation. So this is why we introduce this backward channel H. Okay, so given y hat, right? You transition backward to input X. Okay, so with this one, then you can say, oh, this is, you get another maximization. It's the same thing as the other one, minimization. They actually equivalent. So always apply the divergence inequality. So we can show that. So this condition mutual information is now equal to this maximization over the backward channel of this two-tuple summation. Okay, it's two-tuple summation. Now in this type of summation, you can see, so this condition PDL, condition probability of X given Y does not really depend on the parameter theta, right? Does not really depend on backward channel. Otherwise, you can chop it, doesn't matter. Okay, you can further simplify this. So then you got the equation, the minimization problem at the bottom, right? Now you can further come back. The first term now you can see, well, it's sample additive. So that's good. So that one can fit this parallel computation via GPU. Now the second term, so once this backward channel is fixed, you see, and this one is also sample additive. So as a result, so that can also fit the parallel computation via GPU as well. So now we can also do the alternating maximization algorithm, right? So fixed backward channel, then we can apply the standard backward propagation method through the statistic gradient descent to find the theta capital T, right? Once theta capital T is defined, they come back to solve the inner maximization problem, and that one you can do through the analytic equation, analytic formula. Okay, and so once you train this one, so we call the corresponding teacher, like the dimension of the corresponding teacher, we call this maximal CMI teacher, the maximum CMI teacher. So let me now show you some experimental results. Okay, this one was hard for you to see. Let me see another one. Okay, so this one C5 the teacher and student have different architectures. Now you can see, so this MLL represents the traditional one because we call this maximum likelihood estimation. Okay, and this one MCMI is the we just mentioned, right? You can see, so once we train the teacher, there's not many epoch, probably 20 epoch. Now you can see that the CMI value increased quite a bit. Okay, indeed increased quite a bit, right? Now look at the corresponding student performance. So because once the teacher is trained, you can apply any other KD method. So on this one, you get different KD method. Okay, they're all very complicated. Some utilize distribution, some utilize some interlayer information, some really complicated things. So it doesn't matter which KD method you apply in the KD framework. Once the teacher is replaced by MCN teacher, the performance is always improved. Okay, you can see all improved. In some cases, this one improvement is like more than 3%. And more than 3% gain is quite significant. Okay, so this shows the power of the CMI in this context. And even more interesting is the following. Oh, this is the same thing for ImageNet. I just skip. Okay, I skip this one. So even more interesting is the so-called zero-shot few shot problem. So let me explain. So these two tables. Okay. Now in this setup, the teacher is trained over the entire data set, so which including all labels. On the other hand, the student in the KD framework will be trained over incomplete data set. And so what is incompleteness? Well, for some labels, you don't have any sample data at all. Now in these two tables, you can see this red colored label. So that means there's no data sample from with this red labeled color when you train the students, right? Now look at the traditional case, traditional KD with this traditional teacher. Now you can see for this one, right? Automobile, you can see. So when you do once you do that, the student cannot recognize this automobile at all. The probability is 0. Same for the cat is 0, all zeros, all 0, you see? So for those classes which do not have any samples available for student during the student training, well, the trained student, dear student, cannot recognize anything. On the other hand, without MCMI teacher, it's quite different, quite surprising, you can see. So for this look automobile, so even though student is not trained over automobiles data sample at all, he can still recognize this song with a probability 0.76. Same thing for the others. Now for this one truck, the probability is even like 0.84, right? 84% time can recognize it. It's quite amazing result, right? And same thing can be said about this a field shot. What's field shot is still the same thing. Teacher will be trained, it's trained over the complete training set. On the other hand, the student in the KD is trained with partial data set. But in this case, so each class label, right? For each class, you have certain percentage of data available. But for at least for each label, you have some sample there available. Okay. Now this one you can see, oh, because 5%, you can see the gain from CMI, MCMI is still quite huge, right? So this is 5% gain. Of course, when this alpha is getting larger, the gain becomes a little bit smaller, right? Okay. So this is about the KD amplifying deep learning paradigm. Now, before I conclude, let me mention other type of application of this information quantity in deep learning. An interesting one is that CMI can also be used to build the first ever undistillable models while improving the performance. So let me elaborate this further. So in the KD we just talked about, right? So in that case, so teachers is willing to cooperate with students, right? Because we even want to retrain the teacher to help students. But on the other hand, in other application, the teacher may not want, right, its knowledge to be transferred to student at all, because it takes time, effort, energy, resource, right, to train a large teacher. So that will be property of the company, right? It's intellectual property. So once the teacher is trained, I just provide my service to the end user. I don't want this teacher knowledge somehow to be stealed, right, by my competitor. So if a competitor can leverage this teacher to train, small model, then the small model can perform much better, right? And with less complexity. So certainly, if I'm a company running this one, I don't want my teacher, my model, to be able to distill. But then the question is, how can you build a DNN which is not distillable, no matter what kind of KD method you apply? Because there's so many different KD methods, okay? So it turned out actually the one way to do this, I believe is probably the only way, okay? Is apply CMI. In this case, you need to minimize the CMI across all the spectrum. Then it turns out you do that, the model you train cannot be stilled, cannot be distillable. On the other hand, you can further improve the performance over the classical, over the model trained with classical deep learning. Okay, so here I'll list some recent references about how to connect information theory to deep learning. I don't know my time, so maybe it's August, right time? Okay, so then this concludes my talk. Okay, thank you. Any question?
Thank you, Professor Yang. Especially thank you for explaining deep learning in the language of information theory community. We would like to take some questions from the audience. Yes, please. Pass the mic.
Professor Yang, thank you for your very insightful presentation. So, I have the question because I noticed that the contextual information, the CI, seems can improve the performances across different models like the ResNet, like the VGG and the MobileNet. Maybe the last page, the last one. Yeah. This table, last one. Previous one. Sorry, previous one. Previous one. Also, yeah, this one. Because I saw the contextual information can improve the performances on the deep learning tasks across different models. I saw the mobile net, the VGG, the ResNet, right? So my question is there any relationship between the effectiveness of the contextual information and the model's structure, the model's size, or the number of the parameters? Because I saw that the CAI appears to have more significant impact on some lightweight networks, like the mobile net. But just the slight improvement on some, maybe the larger models like the VGG. So is there any relationship of the effect of the CAI between the effectiveness of the CAI and the model structure, the model size?
There may be some relationship because this really depends on, I think, because this CMI stuff is really coming from this mathematical structure, right? Because if that early mathematical structure behave quite well, then probably CMI may not give, at least at the current level, may not give much improvement, right? So, but one way to further improve, because so far I only focused on this output probability space, but this CMI concept actually can be applied to every layer in between. So we just did not have time, resource to compute that one. So I believe that if we apply that one to even larger model, okay, not simple model, right? You can see more improvement.
Okay, thank you.
Yeah.
Okay, is there any other question? Yes, please.
杨老师您好，我看到您就是引入了一个单米分布，这样就把那个单目标的那个 minimize 变成了2个 minimize。那为什么2个 minimize 就能够更适合在 GPU 上并行计算呢？
好，那我来用中文跟你解释一下啊。你看，我们用从这个第一个情况吧，这个情况。你看，在 original 原来这个 object function 或这个 mutual information 它是一个 global architecture global property 对吧？因为这个这个 SY 是个 centroid 嘛，这个 centroid 它不是 depend on 一个 single data sample 对吧？因为它有 average over all possible data sample in that cluster， right？ 所以这样一来，你这个做起来你就没法做这个 parallel computation， 就是你这个 objective function 它不是一个就是不是它这个 value 不是说我第一个 sample 计算一个 value， 另外一个 sample 计算要把它加在一起的，所以它就我讲的是不是一个 sample additive， 对吧？如果不是 sample additive 的话，那你告诉 minipath 你这个做起来你没法做了，你这个 parallel computation 就跑不起来了啊。那反过来，我要把这个 into the dummy distribution 完了之后，你这个从信息链可以证明，就这个 mutual information 呢，这个正好是等于这个 minimum over QC， 然后在这个 expected value 这个 divergence。好了，那现在 given 这个 QC 的情况下，加上 given 固定以后，你再来看这个 expected value 啊 ，expected value with sub capital X capital Y。这个 divergence 对吧 ？Q sub x and Q sub y， 那这个里面就是说你一个 x y 就是表示它是一个 sample 嘛，一个 data sample 嘛，对吧？因为这个相当于 expectation this over training set， 那就是说你这个是 run over through the whole training sample。那这个 d 这个 function， 那现在毕竟它就是一个什么？一旦我这 Q C 改定以后，它这就是一个 sample by sample base 的，啊，那我这个是跟我原来的 cross entropy 的性质是一样的，那这样呢，我就可以做这个 parallel computation。
哦，明白了，谢谢您。是不是可以证明那个 QC 那个最小值恰好就是那个概率的中性呢？
是的，这是可以证明的，这就是线性论的标准的工具是可以证明这个的。嗯，
明白了，谢谢老师。
Okay, last opportunity. Any more question? Yes, please.
Thank you, Professor Yang, for the wonderful talk. So I have a question regarding this CMI measure. So this seems to be mainly for like the supervised kind of deep learning, like classification of images, or maybe some simple tasks. Recently, there are something called AIGC, AI generated content, mainly use the generation abilities of like large language models, like ChatGPT kind of thing. So do you think this CMI measure is good enough to measure the performance or measure the as a metric to evaluate the generation ability of the large language models?
So yeah, that's a good question. So recently we also trying to apply this concept to the to ChatGPT, for example. That's a large language model, right? I think that is really depend on the problem. Okay, so if for certain this you have certain so-called class concept, then this concept can be applied. And for the other one, probably you modify this concept to fit into that application scenario. Because in our case, right, we just need that this as long as the output of DNN can be characterized as a proposition, then we can look at the proposition space. Okay, maybe the cluster in this sense have for different application between for language, for example, I feed like 2 pieces of text to see whether or not they express same meaning, for example, right? So this also like a binary, more like a binary classification problem, right? But in that case, maybe this class concept may be slightly modified. So information, this quantity can also be slightly modified. So I believe this can be applied, okay, but with certain modification. And one of my master students is looking into this. In some cases, got good result. In others, we have not seen much improvement. But I did not get my own time on that one. I think the quantity need to modify. Okay.
All right. So thank you, Professor Yang, for the wonderful talk again.
Thank you.